Today we will start where we have ended a little bit abruptly last time. The whole video today can be summarized under the headline Properties of the 2D Spectrum, because we will now summarize what we have learned earlier. We will summarize it really in expected properties of spectral features of the 2D spectrum, and then we'll try to associate these spectral features with dynamics that occurs in the observed, spectroscopically observed systems, and we will also try to figure out what other treasures we can find in the 2D spectrum. The first thing we'll try to do will be to calculate the expected peak amplitudes of the spectral features in the 2D spectrum. So amplitudes of the peaks, they are combined result of the strength of the transition dipole moment factor and the weighting with the evolution operators or superoperators. So let's start here in the bottom corner, omega A, that's ground state bleach at A. Ground state bleach at A has no time evolution and it involves all excitations on A. So there will be here a factor dA to the fourth averaged from the ground state bleach and also from the stimulated emission. So there will be two of these things. They are both constant and nothing changes on them. Okay, let's have a look here at AD. There we have excited state absorption from A. So we first excite A and then we go to the excited state absorption. So there will be a minus, but actually the first transitions go to A and the second two transitions go to D. So this is going to be D square A square averaged, and the ground state bleach AD signal will also have plus, and it's gonna evolve, but two of the interactions will be with D and two with A. So we have this sum, which obviously seems to lead to 0. So there will be no crosspeak in this case. Okay, let's have a look at this situation at the bottom. So there is excited state absorption from D. So excited state absorption from D will first of all suffer from a decay of D. So there's going to be this term, and excited state absorption from D means that we excite D, and then to go to the twice excited state we have to excite A. So there's going to be D A square D square, and it occurs with minus. Okay, I'll use some protective boxes so that we don't think that we sum these things together. So these are already finished results, but here we have still just one contribution, the excited state absorption from D. So then there is ground state bleach dA or AD, that's from D to A, which is going to be with plus and no time evolution and two excitations on A and two excitations on D. And plus we have this stimulated emission dA. That is a stimulated emission, so it's plus. The first interaction is at D, the second interaction is A, or second two interactions is A, so it must look like this. And it's a rising term because you emit from A, so you have to follow the evolution of the A. That's this term. We go from D to A with T. Okay, so this is a relatively long expression, and we will have a very similar one also from the remaining peak, which is diagonal. This diagonal peak has a contribution from the stimulated emission of D. Stimulated emission of D must have all interactions on D, so it's this, but it's weighted with the population of the state D, which is decaying. Then there's ground state bleach from D. That's a very simple signal, just D to the fourth power and no time evolution. And then there is a part with minus where we start with D and go to A and have an excited state absorption. So this also has all four interactions with the D. That's because you first excite at D, then you travel to A, and by that you free the D, and you can again excite D. So all excitations occur on D, and this is a rising signal with 1 minus e to the power k a d t. Okay, very long expressions, but they can be relatively easily combined together. So let's repeat the 2D spectrum again, and now finally write some simplified expressions. So this is omega tau, omega t, position omega a, omega d, omega a, omega d, and we definitely have a 0 at this crossing. So let's actually draw the lines showing where the signal should appear. So here we have 0, there's no signal whatsoever. Here in the omega d, diagonal peak has two constant contributions that cancel. Then we have two contributions that add together. There's 2 d to the fourth e to the power of minus k a dt. So this cross peak is decaying. There is a signal here, but it's getting smaller as the time progresses. Then down here we have one peak which is constant again, and it is twice the dA to the fourth power. And the cross peak down here also doesn't look like it's going to be 0. The dipole factor is the same, so it's dA square dd square, and you can see that we have twice the contribution. That looks like 1 minus e to the power KAD. So this is a rising peak, which is in fact 0 at capital T equals 0. So we can see that there are interesting behaviors. This diagonal peak is maximal at T equals 0 and then decays, and this is 0 at T equals 0 and grows with the exponential that we can identify as the energy transfer time. So it's also very important to realize that at T equals 0 there are no cross peaks. There are no cross peaks here, and that's because the molecules are, from the point of view of spectroscopy, non-interacting. I mean, they are like non-interacting molecules, and the only interaction, so to say, that proceeds here that we can see is the energy transfer, but we don't have level repulsion, etc. So this is a very important find, because it also allows us in later stages of this lecture to use this information to show something very interesting about the 2D spectroscopy, how it views the energetic disorder in the molecular samples, the fact that different molecules have different energy gaps. Okay, so now we can see that 2D Fourier transformed spectroscopy can observe, quantify energy transfer. The energy transfer always looks like a transfer of the peak amplitude from a diagonal to an off-diagonal position, because energy transfer is when you excite on one frequency and you emit on another frequency. You can see it nicely on a two-dimensional plot in your 2D spectrum. An extremely interesting and important feature of the molecules that we can learn about using the two-dimensional Fourier transform spectroscopy is their energetic disorder. So by energetic disorder, we mean the fact that the molecules, when they are surrounded by their environment, can have very different local conditions. So for instance, we have two molecules that are basically the same, but their actual energetic position of their states can differ depending on their actual situation and interaction with the environment. So each molecule has an environment which is, for instance, polarized in different ways, contains different molecules or different arrangement of molecules. And the ideal molecule or ideal position of the transitions on the molecule gets shifted, sometimes up, sometimes down, but basically each molecule that we work with has a potentially different transition frequency or transition energy. So different molecules have different environments, and that leads to different transition energies. This is very important because each of these molecules, if we for a while assume that this situation is static, or let's say the changes of the transition energy are slow in comparison to the timescales on which we see the absorption, this means that we see different absorption spectra for different individual molecules. So we can, for instance, assume that here we have an absorption spectrum, omega. Here we record the absorption, and one molecule may have its transition here, whereas, for instance, another molecule, if we would take them individually, would have a transition somewhere here. So altogether, if I combine these two spectra of what is potentially the same molecule, I mean same type of molecule, if I combine them together, I might actually get a sum that has a spectrum much broader than the individual molecules. So if we sum all these together, we could expect a spectrum that might look, for instance, like this, might be broader because under it we have different copies of the same molecules. Of course, for instance, around the central frequency, we will have most molecules because they will have spectrum somewhere near the average value. I mean, here we can also assume that these distributions of the molecules follow some relatively simple law, for instance, that they are a Gaussian, but that's not important. The important thing is that the actual spectrum that we observe in, for instance, absorption spectrum, that it is a sum over many spectra of many molecules that may be a little bit different. This is the disorder. So we can say, for instance, that then the width, for instance, the width of the absorption spectrum is not given by what we have considered so far, that namely by the pure dephasing of individual molecules, but it is given actually mostly by disorder. And by looking at the absorption spectra, for instance, we are learning more about this so-called inhomogeneously broadened line shape, broadened line shape, then about the so-called homogeneously broadened line shape. I mean, each line shape is somewhat broader than the exact resonance. Exact resonance would be basically a delta function, an exact absorption only at the exact transition frequency, but we actually see something which is inhomogeneously broadened and something that is homogeneously broadened. What does that mean, homogeneously and inhomogeneously? Well, the broadening on a single molecule is the same for all these situations. We see a molecule actually absorbing, the molecule 1 and molecule 2 here absorbing on different frequencies, but they have basically the same line shapes. The fast part of the interaction with the environment might, or might not, but in this case it is, might produce roughly the same line shape. Whereas the slow part of this broadening, which we can only see when we sum over the spectrum, is fixed for the molecule, and it's therefore different for different molecules. Imagine that you have processes on the transitions of the two different molecules that are actually unique to the molecules but follow the same rules. So if you take the very fast component of the fluctuation of the transition of this molecule, this will average over the time that it takes to excite the molecule. So let's say the broadening of the absorption spectrum will go in the same way in all molecules. This same way is therefore the homogeneous broadening. And the part of the broadening that consists of the slow motions, that is therefore for the particular event of absorption fixed for the molecule on some value, and each molecule exhibit a different value. That is the inhomogeneous broadening. So we have these two types of broadening, and in the absorption spectrum we can see mostly the result of the inhomogeneous broadening, unless of course both the homogeneous and inhomogeneous broadening results in roughly the same shape. Let's give it one more try in the explanation. Let's assume that we have a molecule with a given transition frequency omega, and now let's plot the transition frequency over time. And in our case, I think it won't matter what type we mean, but let's plot now the transition frequency. Let's assume that it times 0, that's this value, and this is the expected average. So the fact that we have this fast and slow component, or homogeneous or inhomogeneous component of the broadening, looks in this diagram roughly this way. So we start from the average value, and there is very fast fluctuation, or there is a fluctuation that has these two components. One of them, as you can see, is extremely fast, so that it averages to certain value on some small bin. If you take a small binning of that time, we will be able to average the value like this, for instance. And let's assume that, for instance, this is the size, this delta here is the relevant time step in measurement of the absorption. Then we will see once the absorption spectrum corresponding to this bin here, to this bin, we will see it here. They will always be roughly of the same width. So for instance, this bin would be here, etc. They would be of roughly the same width, because the fast part of the fluctuation averages over the size of the bin into roughly the same value always. Whereas the molecules spend extended time, for instance here, to have transition energy of a certain value. So on a very slow time scale, the fluctuations are not visible, or basically with respect to the size of the bin, we can assume that those small fluctuations are slow. There is a constant value within the bin. So this is how most of the absorption spectra actually are built, and from the perspective of the absorption, the size, which corresponds to the size of the bin, the slow fluctuations are actually considered static. This is the so-called static disorder. All right, so with that we can go further, and we can ask ourselves, what are the properties of the 2D spectrum with respect to this fluctuation of energy gap? So we can assume that we replace this time-dependent slow fluctuation basically by an ensemble of molecules that have a distribution of energy gaps, because at every time, so this was just one molecule, but at every time in the sample I have a lot of molecules, and they all have certain position of the spectrum, and I'm averaging over them. So I don't actually have to average over time, I can average over an ensemble, and I can ask myself, what is the total spectrum of an ensemble? What is it? And a very important rule is that non-interacting molecules contribute additively to the spectrum. They contribute additively. So an ensemble of non-interacting entities has a spectrum which is a sum of individual spectra. That's an extremely important result, and it works for absorption spectrum, and it also works for the 2D Fourier transform spectrum. So we can of course find a proof for this proof for 2D EF spectrum. Well, that proof has already been done, and that's actually our considerations here. Imagine that we have KAD, that is the rate of transition from the donor to acceptor, equal to 0. That's the situation in which there is absolutely no interaction between the molecules. There is not even energy transfer occurring. And if you do that, you'll see that the size of the cross peak at all times, capital T, is 0. So the proof is basically the situation with KAD equals 0, and it results in no cross peaks. And we can also remember that there were no cross contributions between the peaks. The diagonal peak actually always contains only signals from a single molecule. It's a little bit more complicated if you look at everything from the point of view of the collective basis. We have seen that the signal at the cross peak actually is the ground state bleach of the cross type compensated by the excited state absorption. But that's just a formal description how it comes about in our perturbative theory. And otherwise, we actually really do not see, or we cannot see, as combined signal from non-interacting entities. Okay, so that gives us a chance to actually have a look at how a 2D Fourier transform spectrum will look for a system with this order. So the next step will be to look at the 2D FT spectrum with this order, and we mean always the energetic disorder. Okay, so let's consider again donor acceptor dimer. We have two molecule entities with transition frequencies omega d and omega a, and these molecules, let's assume them to be non-interacting, and let's have a look for a start at the spectrum at tau equals 0, so no cross peaks. So we know that these molecules have this order, but there might be independently some fluctuations of their energy gaps. So we will have in one case acceptor and donor like this. In another case, let's say for a different molecule at a particular time, we might have them farther apart, or we might have them closer to each other. Looking at it like this is the absorption spectrum. We can expect that if we sum all these spectra and add some more, we will have a relatively broad absorption spectra, for instance, like this. What happens in the 2D spectrum, however? So we know that the line shape is relatively narrow. So in the first case, we are going to get an independent contribution from A and an independent contribution from D at different frequencies. At the second case, we will have the energy of the A lower, so it has to go here because it absorbs and emits on a frequency that is lower than the average. But for the D, the donor, we have higher energy, so we see the peak here. Whereas the third situation leads to higher energy on A and a lower energy on D. The two actually fluctuate independently, so we can draw them at different frequencies completely randomly, and quite clearly at the end we will see a total spectrum that is still narrow in the anti-diagonal line but relatively broad along the diagonal line of the spectrum. And then again, quite intuitively, we can see that the width of the spectrum along the diagonal corresponds to the width of the spectrum in the absorption spectrum, which is the so-called inhomogeneous line width. So we have an inhomogeneous line width in this spectrum, and we find it along the diagonal of the spectrum, whereas in the direction perpendicular to the diagonal, in the anti-diagonal direction, we can still see, roughly speaking, the width of the individual molecule. We can see the homogeneous line width here. So it seems like the 2D spectrum actually offers us both the inhomogeneous and homogeneous line width, at least in the ideal case that we study. So clearly this is a big advantage with respect to the absorption spectra, which can only see the absorption spectrum, that is the information that you get on this plot if you would make it in 3D as hills, and you would be looking at it from this direction. And then projection on one of the axes, that is on the absorption or emission axis, will have the same property as the absorption spectrum. But we are looking at our spectrum from the above, and there we can see both the homogeneous and inhomogeneous line shapes, not just the inhomogeneous one like in absorption spectrum. There are further possibilities how we can use 2D spectrum in our advantage. We can see also other inhomogeneities in the properties of the molecules, other inhomogeneities. For instance, we can see the inhomogeneity in energy transfer. Let's assume that we have again the same situation, acceptor and donor frequencies. And let's assume an assumption which is fairly reasonable that the energy transfer depends on the energy gap between the molecules. So this type of transfer occurs, for instance, only when the molecules are relatively close to each other. So it occurs only for small difference of the energy gap. And then at time larger than 0, what we could see, we would have original spectra looking like this, but the energy transfer only occurs when the two molecules have the energy gap that is close to each other. So for instance, the energy transfer can start here and here at this frequency. So the cross peaks will be here. So a picture like this actually shows something about the inhomogeneous distribution of the energy transfer within the molecules. What should it be compared to? So this is certainly the inhomogeneous case. How a homogeneous case would look like. Homogeneous would mean that in all of our currently investigated molecules in the same sample, the energy transfer occurs the same. So again, having this distribution of peaks, which corresponds to the distribution of energy transfers, we have actually from each point, for instance, from this one to this one, we have the same probability of transferring as from here to here and from here to here. So this means that we would clearly have to have a diagonal cross peak that looks like this. Or what we could see, for instance, another situation in which all the energy gaps or movements of the energy gap of the donor and acceptor were correlated. Well, we cannot see that correlation in the spectrum without a cross peak. But if we, for instance, saw this situation, that this molecule can only transfer energy to this one because they actually moved their energies together, and this one to this one, because whenever you had the donor of higher energy, you also have a donor of the lower energy, and this one to this one, middle to middle, you would see a cross peak that looks like this. Now you already see a third situation. In all cases, this is t larger than 0. In all these situations, you see different type of cross peaks, and all these situations tell you something different about the system. So you can already see that the richness of the 2D spectrum is very large, and that it potentially can bring a lot of information, way more than even pump probe, because again, pump probe can see some, but only some of these informations, because pump probe is a projection of the 2D spectrum on the emission spectrum, so on this spectrum. So we should not underestimate the power of pump probe, but the fact that in the 2D spectroscopy we see all these figures from above and we can easily see correlations between different wavelengths, that's its real strength and its real advantage over some other methods. Okay, we said that non-interacting entities have additive spectra. So this donor and acceptor in our example here are certainly interacting because their spectra are not additive. They have the crosspeak, which originates from some form of interaction which shows up as energy transfer between the donor and acceptor. Let us now consider some more involved type of interaction, namely the so-called excitonic interaction. That is the interaction that actually leads to a creation of different eigenstates than the excited states of the individual molecules. We will be talking about delocalized eigenstates of a complex of molecules. So let's have a look at how the excitonic interaction plays out, or how it shows up in the 2D FT spectrum. Basically, the idea is, as before, this is now interacting a bunch of molecules, so the spectra will not be additive. There must be additional features that distinguish the spectrum of a non-interacting from interacting case. So let's have a look at the excitonic interaction in 2D FT spectroscopy. Okay, so we first have to specify the interaction, what we mean by interaction. So we mean now something slightly different from before. So we mean by interaction some sort of a coupling, which has a coupling energy assigned to it. I mean, in the previous case where we have energy transfer, we haven't specified any coupling energy. There must be something like that, but we haven't seen any spectral features of that in the spectrum except for this relatively slow process of energy transfer. So now we mean something else. We mean so-called resonance coupling. So if we have two molecules with ground states, this is going to be GA, this is the excited state of A, and some excited state of molecule B and ground state of molecule B. We assume that this has an allowed transition. For instance, when EA is excited, it can de-excite, and through the interaction that we consider, through the interaction with the other molecule, it can simultaneously lead to an excitation of the other molecule. So energy is conserved in this system, just the excitation can go from one to another. If we consider the Hamiltonian of this system and use the collective states that we have defined before for description of this system, we will see that we will have a Hamiltonian matrix that will have the ground state energy, which is the ground state of the molecule A, and ground state energy of the molecule B. Then there will be singly excited state, I'd say the case with molecule A excited and molecule A de-excited and molecule B excited, and also the situation with molecule A and molecule B excited. So this is going to be the Hamiltonian matrix. Most of the other elements will be zero here, except for the term that can lead to the switching of energy, or let's say energy transfer between the molecule A and B, and that's this term. So this is the coupling energy J between the two molecules. So we have a Hamiltonian which is now not diagonal in the basis of states that we have used before. It is not diagonal, and the J here will be in general considered non-zero. But let's say, because that situation we already know, so what happens if J is equal 0? Then we have molecules A and B independent. As they are independent, they can be described by collective states, but all the cross terms like cross peaks and so on will be 0. So cross peaks are 0 in particular at t equal 0, so at the initial time, but in fact they will be equal to 0 for all times, because exactly these couplings, when they are small, they cause the incoherent energy transfer that we have considered before. So it's also at t larger than 0. Okay, why is it? I mean, I have already actually revealed that, but if we consider collective states, that will be now important. In collective states, we have the following situation. We have some processes that seem to lead to cross peaks. So for instance, we have this situation when we excite with the first excitation molecule A, then we de-excite it, so this is going to be a ground state bleach contribution, and then with the third pulse we excite the other molecule and there will be an emission on that molecule B. So this is, if we have a look at the Liouville pathways, for instance here, this is the situation that we look at. We are in the ground state in the middle and we excite the B molecule and then we get a signal out of it. So this is a positive signal and should be somewhere on the cross peak. Of course, I have drawn the molecules A and B with the same frequency, but you have to imagine that A and B has different transition frequencies. And now we also have another cross term in which we excite the molecule A actually with the first and second pulses, and then we excite the other molecule and emit. Now we are going to have exactly the same emission as in the first case, and because the other molecule, the A molecule, doesn't emit, it doesn't change the signal in any way. So this type of signal has to be exactly the same, because it also only comes from the molecule B, as in the first case. But now this diagram here produces, because we go here to the excited state, so we are on the molecule A, and then we have another excitation and we emit. You can see that this is a minus sign. If you remember something about the diagrams, if there is an arrow from the right, there is going to be a minus sign. We have two arrows or in the first case with the ground state bleach, and we have just one arrow in the excited state absorption situation. So there is a minus sign, and these two signals that would give us a cross peak, they equal to 0 together. So this is what happens in the collective states if there is no coupling. So this is the situation of J equals 0. But we will be far more interested in a situation where there is no such compensation, where the coupling J is much larger than even in the small j case, which led to the slow transfer, which we could describe by some energy transfer rate. So there is a situation when there's a so-called delocalization of states. So this is the situation if J is large, really large, not just larger than 0. Well, in fact, it has to be larger than 0 in absolute value. And what happens in this case? Well, in this case, very often one can see that the eigenstates of the Hamiltonian are no more those simple collective states that we have defined before. So the eigenstates of the Hamiltonian are delocalized. Why is that? If you imagine this, if you take this this Hamiltonian here and want to diagonalize it, that is to find its eigenstates, you only have to diagonalize this middle section. You basically just have a problem of diagonalizing a 2 by 2 Hamiltonian with the energies of the molecule A alone and molecule B alone and coupling J, and you ask what's the result of this eigenproblem here. Well, you can verify. Let's assume for simplicity that we only have one energy in all this, and the eigenstates will be such that they will be a symmetric superposition of the states A and B, for instance like this, and there will be an antisymmetric superposition of the states A and B also working easily as the eigenstate of this Hamiltonian. I mean, just to prove it, just to see that this is true, you can try the following. So this is going to be the up to the normalization factor. This is the symmetric situation, and you can easily see that this is epsilon plus j and epsilon plus j, which is nothing but the energy, the eigenenergy. So some sort of epsilon plus equal epsilon plus j. Or if you try that for the antisymmetric situation, that's here, you get epsilon minus j, and here you get j minus epsilon, which is nothing but epsilon minus j multiplying 1 minus 1. So this here is the epsilon minus energy. So what we get is the energetic splitting, and we get a possibly completely different composition of the eigenstates. And now we have to look at where we find the spectral features, or how we can actually estimate how is the 2D spectrum going to look like. So state diagram based on which we will try to estimate the positions of the spectral features. The state diagram is going to look like this. Here we will have the original energy epsilon, and it will be split up and down by j. So we can see two transition energies from the ground state. One of them will be epsilon minus j, and let's say from here to here, from the same state up to the 2 exciton state, which is 2 epsilon, we are going to see epsilon plus j. And also here from the ground state we see epsilon plus j, and from here to here there is going to be epsilon minus j energy. So as before, we have two energies on which we can expect spectral features, some omega minus, omega plus, omega minus, omega plus. So we can denote these states with ket vectors minus and plus, and obviously the transition energies are h bar omega minus and h bar omega plus. Anyway, so looking at this state diagram, we can see that we will have two excitation frequencies, omega minus and omega plus, and two excited state absorption frequencies, at which we can see also the signal produced, and those are also omega minus and omega plus. And obviously we can have processes of ground state bleach and stimulated emission on omega plus and omega minus. So it's gonna be here. In both cases it's ground state bleach plus stimulated emission, ground state bleach plus stimulated emission. And we can also have excited state absorption, but excited state absorption, for instance, starts on omega plus and continues on omega minus. So excited state absorption can only appear here and here. This is excited state absorption. And then we can have the excited state absorption cross terms potentially, but here in this picture this is somewhat more complicated. So when we had two molecules and we could look at situations when one molecule was excited by two pulses, that is entirely excited, then we could excite the other molecule because its ground state was intact. But in fact, this procedure or this process corresponds to the excited state absorption that we have just described. Because by exciting one molecule, you are getting into a singly excited collective state. So once you get to a singly excited collective state here, there's no possibility for another ground state bleach signal. But you can have a cross ground state bleach signal. That is, first pulse you excite plus, for instance, de-excite to ground state. So the signal will be on the omega plus frequency, at the excitation axis. So let's write here the two omegas of the excitation and emission frequency. So let's say we started at omega plus, and the cross signal is on omega minus. That is, we first address the state plus and then we address the state minus. So that signal will appear here, and that's the ground state bleach, but let's call it cross. So that's one signal which involves both plus and minus states. And the same situation occurs also here. You can first excite, let's say, create a bleach on the minus state and then address the plus state. So there is plus GSB cross here also. So there is a very important thing to add here, that the excited state absorption is a signal which has a minus sign in both cases. And the question is, what happens to this peak? How is this going to play out? Who is going to win? Is it going to be ESA or ground state bleach? And we've seen in a situation where these collective states described two independent molecules with no interaction energy J, we saw that these two contributions actually exactly cancelled each other. So there were no cross peaks. Now, it would be strange if this was also the case in the case of the delocalized states. We have started to study a special case in which we have a perfect delocalization. We have states that are maximally delocalized. Each of the A and B states actually gives exactly 1/2, or has the probability of exactly 1/2 in these eigenstates. But that still does not mean that we know exactly how the strength of the transition dipole moments are going to look like. We will talk about it right now. We just have to remind ourselves that in the case that the states that we are looking at were not delocalized, then we saw that the amplitude of the excited state absorption and this cross ground state bleach was exactly the same, and it cancelled, and the absorption, or the 2D spectra, of course also the absorption spectra of the two individual molecules that we've discussed, they just added together and there were no cross peaks therefore. So in this case, it seems to be quite clear that it would be a very unique situation if we had the two cross peaks or the two signals cancelling. So we can conclude that there is going to be an off-diagonal signal, and that off-diagonal signal will be the thing that distinguishes the 2D spectrum of a coupled dimer, that is two molecules that are coupled by some resonance energy J, from a situation that we have a dimer in which this coupling is either very weak so that we can't see it resulting in delocalization, or it's basically absent. There can be easily a complex of molecules which are so far apart that their interaction is negligible, yet it's a complex of molecules. So there we can't find anything, but in a complex of molecules that are held together close enough so that their excited states interact, we expect in the two-dimensional spectroscopy some cross peaks to appear at, and that's very important, at t equal 0, because cross peaks can occur also in a cross peakless situation, but at t larger than 0 due to energy transfer. In here, in this situation, we will have both energy transfer, which probably will change the peaks and including the cross peaks. That's what we will have in this situation, but at t equals 0, we can also see cross peaks appearing because of the disbalance of the excited state absorption and this cross ground state bleach. So now let us have a look, how is it with the transition dipole moment strength for the transitions that we have here. So between the ground state, the plus and minus states, and the doubly excited state, which we call F. We define transition dipole moment operator for the system of two coupled molecules, for which we have written here this state diagram in its delocalized states. So transition dipole moment operator. So that's what we need to look at in order to be able to find out how we can transform the transition dipole moment into the delocalized states, to figure out what are the strengths of the transitions and what are therefore the comparative strengths of the excited state absorption and ground state bleach that we see here. Okay, so the transition dipole moment operator has to be written in terms of the collective states. So we will have transitions on the molecule A in our two molecule system, and there will be a transition from state with the molecule A excited and B not excited, and that is a transition from the ground state. There will also be a transition on the molecule B alone, so we go from G to B, and there will be a transition from a situation where A is already excited and therefore we excite B again to reach the state F, doubly excited state F, and in that case we started from A. And there is also a situation in which we start from B and go to F, that is, we excite the molecule A. And of course this is only one side, one allowed process. This is always from the lower state to the upper, and we have to add the Hermite conjugated term, which contains the terms for the de-excitation. So this is the transition dipole moment operator, and because we know how the plus and minus states look, we can also see how the A and B look in terms of the plus and minus states, and we can therefore rewrite the transition dipole moment operator in terms of the delocalized states. So we can, for instance, see that when we add plus and minus states, we get the A state. So we know that the A state is 1 over square root of 2 plus minus, and correspondingly B is going to be, and now let's just get the order right. So we have to take plus minus minus state. So plus minus minus, this is going to be B, and this is what we can use here in the definitions of all states to figure out what are the transition dipole moments for the transitions from, for instance, from the ground state to the state plus or minus. So for instance, we have mu, let's start with a different color because this is going to be interesting. So here we have a vector. Vectors become very important now. So the state A is written as plus minus, and the state B is written as plus minus, and well, this is all going to be with G here, and now we will have F and D B square root of 2, and A is plus minus, and here we have dA square root of 2 plus minus. Okay, putting all this together, if we want to collect the states with plus, we are getting dA plus dB square root of 2 is a transition from G to plus, and we collect this and this, we have dA minus dB square root of 2 minus G, and we also have dB plus dA square root of 2, and this is a transition from plus to F like this, and here we have dB minus dA square root of 2 and F minus, so a transition from minus to F. So I mean, we can see clearly that the transition dipole moments add and subtract from each other, Now it very much depends on what is the direction of the transition dipole moments of the two molecules. So if we assume, for instance, that they have some very general spatial direction, so they are located here at these 2 points. So this is X, Y, Z, and these are the locations of the molecules, and these are the transition dipole moments. We can see that none of these transition dipole moments are actually in general zero. There might be very special situations, for instance when dA equals dB, for instance, in which case we have some of the transition dipole moments, we have d plus, which would be square root of 2 dA if we choose, for instance, and d minus would be 0. For most of the situations, we, however, can basically only observe that the transitions from G to plus and the transition from plus to F have the same transition dipole moment, and the transition from G to minus and the transition from minus to F are basically also the same. There's a minus sign here, which is not very important. But what we actually have to ask now is, how is this going to be important for the amplitude of the crosspeak? So let's ask, what's the amplitude of the crosspeaks? So the amplitude is always given by the difference between the excited state absorption, which comes with minus, so there's always minus excited state absorption, and plus the ground state bleach of the cross type. So that means, if we make a miniature of our diagram before, we have the transitions involved in excited state absorption. For instance, let's start with the crosspeak that has the excitation energy higher. So this is here the first two excitations going here, and then there is an excitation to the state F, and the emission comes from here. So this has a factor, the dipole factor, basically d plus square, because in our diagram the plus state is the upper one. Okay, so the plus square, and we see that d plus, this is d plus occurs also for the transition plus to F, so this is also d plus. Okay, so eventually actually we figure out that this is d plus to the fourth with minus. And now the second element or second pathway that contributes to exactly the same place is the ground state bleach. Ground state bleach is this process. We excite the plus, we de-excite back to the ground state, and then we excite again to the other state, to the minus, and that state emits for us. So we have two transitions going to d plus squared, and then the other transition is in general different. So this is d minus, and this is minus d minus. So we altogether get twice the d minus state. So that's here, twice d minus. So this is d minus squared. And that is in general different from 0. So, I mean, of course, we have also some other factors here, but let's say if these things appear in the same spot, the fact that they might even have slightly different line shape is already really minor in comparison to the fact that the prefactors of these contributions might be completely different. So this is not 0. And we have obviously the amplitude of the crosspeaks dependent on the difference of the transition dipole moment values. So we can conclude that in general, crosspeaks in a 2D spectrum at t equals 0, this thing here, are signs of the coupling between the molecules that compose the system that we observe. So we can basically see here whether the states that we observe on the diagonal, we observe basically their direct signal on the diagonal, we can see whether they are delocalized, that is, whether they are formed by some interaction between the excited states of the molecules that form the complex. We can find that out by non-zero crosspeaks of the 2D spectrum. Okay, that can lead us to some sort of a summary about the properties of the 2D spectrum. Basically, the main properties are the following. So the 2D spectrum, well, it's a very powerful method. 2D spectrum shows delocalization, that is resonance coupling between the molecules. It shows it by the presence of crosspeaks at t equals 0. So at 0 delay between the first two pulses, or let's say the second pulse, and the third pulse of the sequence. So we also can say that it shows energy transfer by evolution of crosspeak and actually diagonal peaks, but crosspeaks are the most important. Evolution of the crosspeak amplitude as a function of time, so it's the t larger than 0. And the third thing that is quite important and interesting is that it reveals homogeneous and inhomogeneous line width at t equal. Let's put it like this. It reveals the homogeneous and inhomogeneous line width. This information about time, that's something that we do not have much right to speak about now, because the homogeneous line width evolves in time, and we have actually no theory for that at present. So the homogeneous line width evolves with time, and with the present theory we do not see any way how this could evolve. But that's because we have made some relatively crude approximations at the very beginning, where we've decided to work with the reduced density matrix. And in one of the following videos we will go back and try to see where potentially we can have a breakdown of the approximations that would give us that basically prescribe us or give us this confidence that we see homogeneous line width in the 2D spectrum. The truth is that this homogeneous line width evolves with the time t, with this difference between the second and the third pulses. Despite all these great properties, two-dimensional Fourier transform spectroscopy became actually famous for something completely different, namely for its ability to detect and analyze electronic coherences. So let us first discuss what does that mean, or what is electronic coherence, and by analyzing a certain set of Liouville pathways that we have so far not considered, we'll be able to see what kind of a picture of electronic coherence we should see in the two-dimensional spectroscopy. So the topic is electronic coherence in 2D FT spectroscopy. So what is it first? Well, let's draw again the state diagram that we have with the ground state, with, let's say, the minus, plus, and F state. And let's imagine that our laser pulse is so broad spectrally, that is so short in duration, that we can excite simultaneously both the state plus and minus. Actually, this has to be the case, because otherwise we won't see them in this pulsed version of the experiment in one spectrum. Now that means the fact that we excite plus and minus at the same time means effectively that we actually excite their superposition. So the initial state of this system should be a superposition of the plus and minus states. That means that the initial density operator or initial statistical operator, the density matrix, should contain also off-diagonal elements. This is going to be basically a square as the probability of finding the plus state, b square as the probability to find the minus state, and there's gonna be a star b and a b star complex conjugated off-diagonal elements of the density matrix. For instance, we can denote them this way. So this is the element plus plus, this is the element minus minus, element plus minus, and element minus plus. These things evolve in time, and the terms plus minus evolve roughly as some, they take some value at t equals 0, and then they evolve with I omega plus minus t. So what we have here is the time evolution of the phase with the frequency that corresponds to the difference of energies between the states plus and minus. So the fact that the non-diagonal off-diagonal element of the density matrix is non-zero corresponds to the fact that you can describe it by a pure state, or at least partially pure state, which has to be written in quantum mechanics as a superposition. So this is a coherent superposition of the states plus and minus, whereas in the case that these terms decay to 0 and at some very long time, longer than some decoherence time, we will have a diagonal density matrix with just the populations and off-diagonal elements equal to 0. This is the process of decoherence or dephasing can actually lead to this. In this case, we cannot write anymore the state of the system described by the density matrix as a wave function. It's an incoherent sum of the wave functions. Well, in fact, it would have a form like this. This density matrix corresponds to this expression using Dirac notation. Yeah, so once we lose the elements, the off-diagonal elements, because they decay by some rate, once we lose them, we get a so-called mixed state. This is like completely mixed state, whereas this thing is a pure state. And we have, basically every state that is not completely pure is mixed, but here the state that we end up with at very long times, it has zero purity. There is not a section of it that could be called pure. The details of this are not so important. It is important that we can see the oscillations corresponding to the time evolution of the coherence between the states plus and minus in the 2D spectroscopy. And we call this coherence electronic because the states that we look at here are electronic states. If we were looking at states of some harmonic oscillator of, let's say, molecular vibrations, it would not be called electronic coherence. Okay, so this is the electronic coherence, and now let's see where we can find some phenomena in the 2D spectroscopy that are related to this coherence. And in fact, we can find them relatively easily if we just look at the pathways, Liouville pathways, that in its middle interval, that is in the interval in which the system evolves in the excited state, for instance, and it has to be excited state, otherwise this superposition of plus and minus states would not be involved. We have to identify those Liouville pathways which lead through excited state and contain some traces of this coherence. And that's actually not so difficult, because we can look at all the pathways that go through the excited state. So T evolution of pathways going through excited states. If we look at them, we find that there is stimulated emission signal and excited state absorption signal, where normally we expect that we go through the population state. So we have the elements of the evolution superoperator of the type of, for instance, plus plus, minus minus, or let's say even plus 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 plus. If we read these from right to left, then we see that the first one is the transfer of the population from the plus state to the state minus, and we have also that part of the dynamics which corresponds to the population staying at plus. But this is not all that is possible. There are also allowed elements of the time evolution that look, for instance, like this, and this is the evolution of the coherence plus minus. We only assume that these terms decay. We do not assume that they transfer to other states, because we still work with the so-called secular approximation. All right, so in the secular approximation, we can expect additional Liouville pathways. That could potentially give us the signal related to the coherences. So let's go through all the pathways that we have. So we know that we always have rephasing and non-rephasing pathways in some sort of a pair. Now we'll see that this pairing will become a little bit problematic, because let's see, our rephasing pathways always start with excitation from the right hand side. So we have the G states, the ground states, and let's excite to plus. We excite to plus, so we have a G plus coherence first, and now we want to go to the excited state, but not necessarily to the population of plus, but we want to create the coherence minus plus. This is no problem. This is going to evolve as e to the power of I omega plus minus capital T, and of course there is going to be some decay also, but we will not consider decay now. We just need to know that we decay. But in the time evolution here, the most important signature of the coherence is this evolution with the frequency corresponding to the difference of energies between the plus and minus states. So this evolves, and now we need to come with another pulse. And what we want to do, we want to get a rephasing signal. That means in a rephasing signal I have to have G here, so I have to go out like this, and I have minus here, and I shine minus. So this contribution very clearly has to end up in a crosspeak, because it emits on the frequency omega minus, whereas it was excited on the frequency omega plus. So this is a crosspeak signal. This is a crosspeak signal, but let's have a look now to the corresponding non-rephasing case. In the non-rephasing case, I will start always from the left, so this is the first interaction. And now I can choose whether to start with plus or minus, but imagine that I want to see the same coherence. So if I want to see the same coherence, I have to start with minus. So I've decided that my non-rephasing pathway corresponding to the same to this rephasing diagram will be the one with minus. So they stop to be actually involving identical states in this case. So the next interaction has to bring me to the excited state. So I'm having the same coherence as before, and I can get rid of the excitation on the right hand side, and I have a minus signal. So this signal, however, although it has exactly the same coherence and everything, it ends up on the diagonal, because we excite it on omega minus and we emit on omega minus. This is a diagonal signal. And it's clear that if I start with minus here on the rephasing side of it, I will end up with a different phase of the coherence. So now I have minus I omega plus minus t and possibly some decay, and this will correspond to a different cross peak, to the opposite cross peak. So this is also a cross peak, but clearly we start with omega minus and end with omega plus. And if we decide to do on this side the same thing with non-rephasing, which starts with plus, we also again end up on the diagonal. So there is no way concerning just these pathways from the non-rephasing part how we could get a non-diagonal signal. So this is also a diagonal signal here. Okay, so the only thing that we are still missing, so this was the stimulated emission. Ground state bleach doesn't have to be considered because in the ground state bleach we do not see any coherence. We start with one state and we drop back to the ground state. So the only other situation that has to be considered is the excited state absorption. And actually, considering that for the situation in which the coherence should not matter, that is in a situation where we should not see cross peaks, for instance, and that's the uncoupled case, I have to have excited state absorption perfectly cancelling with something. I will expect that it has to, because there's no ground state bleach that could cancel this contribution, I will have to assume that it will perfectly cancel with the available signal already, with the one that we have here. So I can expect that even in the excited state absorption, I have to follow basically the same type of rules, and I will have cross peak from the rephasing and diagonal peaks from the non-rephasing. So also it's clear that somehow we have to have four possible diagrams from the excited state absorption. So let's start from the rephasing. On the rephasing we can start with plus, we will have minus by the second interaction, and then we have to go to F. But because we are in the rephasing situation, we have to have the opposite phase, so to say, in the last interval. So F has to appear here. So this is the diagram that leads to the excited state absorption, and it has omega plus here and omega minus here. The frequency between the plus and F state is omega minus. Or we could have started with omega minus and end up with omega plus. So there are two rephasing pathways, and they are obviously cross peaks again, because they have different frequencies. And here on the non-rephasing side of it, I start, for instance, with plus, I go to plus minus with the second interaction, then I want to go to F because I need to have now the same phase, same direction of the oscillations. So this is F and minus. So it is, and because the frequency between F and minus is minus, we have a diagonal peak. So this is F plus, well, F and minus is plus, so we have omega plus, or omega minus, omega minus. So altogether 4 pathways, 2 on cross peak, 2 on diagonal peak. Okay, so we can see that there are pathways that carry the same line shapes as all the pathways that we had before, but in the middle interval they show this very interesting complex time evolution in t. So obviously at different t's we will be seeing sort of cosine type of a projection of this complex exponential into the real part of the spectrum. So in the real part of the spectrum, some part of the amplitude of the cross peaks, the one that comes from these coherences, will have to oscillate. So we can conclude that we, by necessity, when coherence is present, we will see modulations of all peaks. So let's draw the expected 2D spectrum. So we have again the frequencies as before. We have these 4 spectral positions to which these pathways contribute, and we can see that, for instance, we can have, for the minus minus situation, that's a diagonal peak. Minus minus situation would mean that we have e to the power of minus I omega plus I t, and in the plus plus situation, that's the one here on the diagram. Oh, sorry, so here you will have plus, and here we will have minus I omega plus minus capital T. So again, the convention usually is that the positive frequency is in the e to the power of minus I omega t. So then the contribution from the excited state absorption on the diagonal peak plus, that's the one here, will be positive. So here we have plus, and then we have also diagonal peaks again. This diagonal peak here has minus omega plus minus t, so this is also contributing with plus, and here we have minus minus, which contains the minus factor. So we can say 2 pluses here, 2 minuses here from all the pathways that we have looked at. And on the off diagonal that originate all from rephasing pathways, we can find correspondingly down here at the plus minus. At the plus minus we have minus, and we can go up here when we look at the plus minus, we have minus, because e to the power of I omega plus minus t, that's the one with the negative frequency. So this is minus minus, and you can check that you get plus 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 here. So we get contributions that all carry the same phase factor, and you can see that what should oscillate, what should be modulated by these phase factors are both cross peaks and diagonal peaks. It's possible that it is easier to measure the oscillations on the cross peaks, maybe because the intensity of this static contribution to the peak is small, and we might see actually changes from minus to plus. That depends on the strength of the standard cross peaks. But I mean, the important thing about this is only to be able to see and prove that something oscillates, and we can possibly also measure the lifetime of these coherences by seeing how the oscillatory features go slowly away. So an interesting thing is also that we have this distinction between the rephasing and non-rephasing pathways, so that we can go and check whether it is the non-rephasing pathways that oscillate on the diagonal, and also whether it's really truly the rephasing pathways that only oscillates on the diagonal, because we can physically separate rephasing and non-rephasing signal, and we can check that, let's say, only rephasing pathways or rephasing signal, we measure no pathways, we measure signal, only rephasing signal oscillates on cross peaks, and only non-rephasing signal oscillates on diagonal peaks. The fact that we can separate it is given by the fact that rephasing and non-rephasing pathways are obtained when the pulses, the first and second pulse, come in different orders. So we measure them like that, separately in fact. So you can check that the coherences or the oscillations that you see in the 2D spectra satisfy this condition. It is also true that there are other sources of oscillation that we have not discussed yet, for instance the presence of some vibrational modes. in the system, and those should not have or should not follow these rules. They follow some other rules. So there are some ways how, by carefully analyzing which part of the spectrum oscillates in which places of your spectrum, it should be possible to distinguish electronic coherence from some other type of coherences. So we can conclude a very important property of this 2D spectrum is that one can measure the lifetime of electronic coherence by 2D FT spectroscopy.